Have you ever wondered where matter comes from, or if it can just disappear? For centuries, these questions have puzzled the brightest minds. The ancient Greeks believed everything was made of earth, air, fire, and water. They weren't entirely wrong, but they were missing a key ingredient: energy. In the 18th century, scientists discovered something fundamental. Matter cannot be created or destroyed, only transformed. This is the law of conservation of mass. Around the same time, they uncovered another secret energy also obeys this rule. The law of conservation of energy tells us that energy, like matter, is always conserved. These laws hold true in our everyday experiences. Burning wood doesn't make it vanish, it transforms it into ash, smoke, and heat. The total mass and energy remain the same, just in different forms. But could there be a deeper connection between these two fundamental entities? For a long time, the atom was considered the smallest indivisible unit of matter. The word itself comes from the Greek atomos, meaning uncuttable. But as scientists dug deeper, they found the atom wasn't so simple after all. In the late 19th and early 20th centuries, a series of groundbreaking discoveries shattered our understanding of the atom. First came the electron, a tiny particle carrying a negative charge. Then came the nucleus, the atom's dense, positively charged core. Protons and neutrons, the building blocks of the nucleus, were soon to follow. But the quest didn't end there. Scientists discovered that even protons and neutrons are made of even smaller particles called quarks. These quarks are bound together by gluons, particles that act like cosmic glue. The universe, it seemed, was like a giant, intricate Lego set, with particles connecting to form everything around us. Classical physics, with its neat laws of motion and gravity, could explain the world around us quite well. But as we delved deeper into the realm of the very small, a new picture began to emerge. This is where quantum mechanics, the physics of the subatomic world, takes center stage. One of the most revolutionary ideas of quantum mechanics is that particles can also behave like waves. Imagine the surface of a pond. A pebble dropped into it creates ripples that spread outwards. These ripples are like particles, disturbances in the fabric of the pond. In a similar way, particles like electrons and photons can be thought of as disturbances in quantum fields. These quantum fields aren't just abstract concepts, they are fundamental aspects of the universe permeating all of space and time. And within these fields, something amazing happens. Energy itself can spontaneously transform into matter, creating particle-antiparticle pairs. These pairs can then annihilate each other, converting back into pure energy. Einstein's famous equation, E=mc2, is more than just a mathematical formula. It's a profound statement about the nature of reality. It tells us that energy and mass are not separate entities but two sides of the same coin. This equation underlies the most energetic processes in the universe. In the heart of stars, immense pressure and heat fuse hydrogen atoms into helium, releasing tremendous amounts of energy. This is nuclear fusion, the process that powers the stars and creates the building blocks of our universe. On a smaller scale, particle accelerators like the Large Hadron Collider smash particles together at near the speed of light. These collisions recreate the conditions of the early universe, allowing scientists to study the fundamental nature of matter and energy. The universe, it turns out, is not a static collection of objects. It's a dynamic dance of energy and matter, constantly transforming, creating, and annihilating. We are all part of this cosmic dance made of the same stardust that was forged in the fiery hearts of stars billions of years ago, and it all started with a spark of energy.